webinar of Cybersecurity Awareness Month webinar series brought to you by Canadian Institute for Cybersecurity of University of New Brunswick. And today we have another interesting topic waiting for you. And let me introduce the speaker and also the title. So we have Dr. Vikas Chouhan, who is going to talk about beyond classical versus post-quantum, a hybrid approach for the quantum era. And Dr. Vikas is currently a postdoctoral fellow at the Canadian Institute for Cybersecurity. He received both MTech and his PhD degrees in computer science and engineering from the Indian Institute of Technology, Roorkee, India. He has several research publications in reputed journals and conferences. He served as the program committee member and reviewer of several international conferences. And his research interests include cloud computing, cloud security and privacy, information security and reliability, blockchain technology, and post-quantum security. Over to you, Vikas.
Yeah, thank you, Windhya, for introducing me. So let me share my screen. So hello, everyone. My today's presentation topic is Beyond Classical versus Post-Quantum, a hybrid approach for the quantum era. So these are the outline of my presentation, where in the background, I will discuss quantum computing and their threats. And after that, I will discuss classical versus post-quantum cryptography, their security strength and challenges. Then I will deep dive into the hybrid approach for key encapsulations, hybrid signature, hybrid mechanism for public key infrastructure, and their implementation. Then I will provide some recommendations, and then finally I will summarize the presentation. So here, the quantum computing, a quantum era. That means it refers a hypothetical future period of time in which quantum technology such as the quantum computing, quantum communication, and quantum sensing become widespread and revolutionize many aspects of our lives. So here, quantum cryptography, as we know that is based on the quantum mechanical phenomena, which can pose the threat to the modern public key encryption system. So there are so many threats associated with the arrival of quantum computing, like cryptography. Cryptography is one of the biggest threat of quantum computing because many encryption algorithms that are currently using we considered as a secure against the classical computers. So that are broken with the some algorithms and the arrival of quantum machines. So it can be another threat is like a data breach. That means they have the potential to be used to break the current systems and steal the sensitive informations. And the quantum computing can be used to create a super intelligence AI system, which could pose a risk to humanity as well. And another threat is in financial instability. That means it can break the financial institute and manipulate the market as well. And another is the energy consumption. That means the quantum computers require a significant amount of energy to operate. So this could increase the energy consumptions and associated carbon emissions, etc. So, and there is another threat in the cryptography like harvest style threat. That means the attackers are now capturing the ciphertext and store in somewhere secure place, and it will decrypt later once they have the access of the quantum machines. So these are the possible threats, and there are so many vulnerabilities, impact, and risk associated with the arrival of quantum computers. Like it can compromise the sensitive informations and cause the financial loss. It can force the digital signature, which can lead the issue of identity theft because digital signature are used to validate the authenticity of digital documents. It can undermine the security of high level communication channels. It can control the blockchain network and modify the transactions because the blockchain network is depend on the majority concept. So using the quantum machines, it is possible to compromise the number of peers, compromise the consensus mechanism used between the peers, and it also compromise the IoT network and gain access to the sensitive data. So there are so many pros and cons associated with the arrival of quantum machines. Like Symmetric cryptography is not in danger. That means the symmetric cryptography still survive with the longer key size, which cannot be broken by the quantum machine easily. It can reduce the security strength, so we can use the longer size to maintain the security level. Another is the speed. Yeah, the quantum machines is exponentially faster than the classical computer, and efficiency means has the multiple computations can perform simultaneously compared to the classical machines. And the cons are asymmetric cryptography is broken because using the source algorithm, all the factorizations problem and discrete logarithmic problem based algorithms are easily broken. Another issue is the technical challenges because the quantum machines is very sensitive to the environment, so it required the proper cooling mechanism, proper error correcting mechanisms to functions correctly. Of course, high cost is also associated with the quantum machines, uh, and we cannot neglect the security risk as well, which is introduced by the quantum machine. So here we can expect when we can expect the large scale quantum computers. So here we can say that the Global Risk Institute recently published a quantum threat timeline report in 2022, which presents the estimate the likelihood of the quantum uh, computer will be able to break the RSA 2048 in 24 hours. Means this document present the results of survey conducted by the Evolution Q Corporation with the participant of 40 internationally leading expert on the quantum computing. So here we can say that there is an optimistic interpretation is the 50% of likelihood in 10 years and more than 50% likelihood in the 15 years. So here you can see that there is type of cryptography like asymmetric cryptography and symmetric cryptography. So in the asymmetric cryptography, there are algorithm RSA and ECC with the different strength. So here the equivalent to the classical bit security are presented in front of them, but that is equivalent to 0 bit quantum security because of source algorithm can break all the asymmetric cryptography. So we cannot consider all these asymmetric cryptography secure anymore. But in case of symmetric cryptography, we still survive with the longer key because the using the Grover algorithm, it is reduced up to the half. So here you can see that the AES 128 has the 128-bit classical security, which is equivalent to 64-bit quantum security. Similarly, for AES 256 is reduced up to the 128-bit quantum security using Grover algorithm. So we can say that symmetric cryptography is still surviving. So because of this issue, the NIST started a post-quantum cryptography uh, competitions. So initially, the 69 algorithm submitted in the round one, and it will reduce to 26 in round two, and in the round three, we had 15 algorithms, and now we have only 8 algorithm in round four. So these are the NIST selected algorithms and round four candidates. So in the green color, which represent the winners candidate and which are in the process of standardization. And in the blue color algorithm are still part of the competitions. So here you can see that we have two category like KEM category and signature category. In the KEM category, we have the winner is Crystal Kyber algorithm, only one. But in signature category, we have the three algorithm like dilithium, Falcon, and Sphinx. And we have four algorithm in round four, which are still the candidate of the competitions like MakeLEC, HQC, and Bike and Psych. But after the announcement, the few week of announcement, the psych is simply broken with the classical machines. So we are not considering secure anymore for psych. So we can say that only three algorithm is in round four. So here in the background, I can say that the classical algorithm. So we have asymmetric cryptography that uses the key pair for are already broken, and symmetric cryptography is weakened. So there is pros and cons associated with the classical cryptography, like proven security, means the widely used algorithm, the classical algorithms, their security are well tested and established over the time. So that's why we can say that it is has the proven security. And efficiency means it can be implemented with low computational costs, and it has interoperability, means we can use in any system and platforms. But the cons is vulnerability to quantum computers, because the quantum computer can break and weaken the classical security, and it has the limited key size. For example, if we are talking about the AES algorithm, we have only three options, like we have 128-bit key, 192-bit key, and 256-bit key. And for security vulnerabilities, like still has the some security issues, like chosen ciphertext attack and side channel attacks. So the post-quantum cryptography is basically designed to provide the security against both classical and post-quantum algorithm, the quantum attacks. So it resists the uh, against the quantum attack required protections, and we can say that it is a today's defense against the tomorrow's quantum hacker. And it has the unknown impact on the code base, like a larger key size, larger message, and larger signature size. So it can reduce the efficiency of system, reduce the running time, and it can impact on the code agility. We cannot easily migrate because due to the huge sizes of key messages and signature. So the post-quantum cryptography needs longer time to replace and specify in all existing standards like TLS, SSH, Internet Key Exchange, Public Key Cryptography, and SMIME. So the pros and cons associated with the post-quantum, like it provides the security against the quantum attacks. Yeah, it also provides the long-term security, means when the quantum computer arrive, it still work. And it provide the compatibility with existing system, means we can use with the classical computer and classical systems. And the cons is limited maturity, because the post quantum algorithm are not yet mature as the classical cryptography algorithms, and therefore it may be a target for attackers and may be a vulnerable for the new attacks. It required the high computational cost because of its huge sizes. It has limited interoperability because the post-quantum algorithm required the huge redundancy, huge overhead is there. So these are big in size, so cannot be easily um, used with any system, like resource constrained device can't support the post-quantum cryptography right now. So here, the classical cryptography, which are widely used and well established, they may not be able to provide the long-term security when the quantum computers become the more powerful and widespread. So uh, in because of these reason, NIST introduced the 128-bit symmetric security strength, which provide the security until 2013 and beyond. So it is must be recommended by the NIST that everyone should consider equivalence level of security. At least 128-bit symmetric key security should be maintained, so it will survive till 2013 and beyond. So NIST provide the different level of security, like you can see here, different 5 level of security from 1 to 5, and based on the different algorithm equivalency. So here in the chart, you can see that there are several algorithms, like all asymmetric algorithm are broken, so they are not secure anymore. And all red color algorithm are not provided at least 128-bit classical security. So therefore, we can consider the algorithm which is represent in the green color, which provide the at least 128-bit quantum security. Similarly, here in the post-quantum security strength, we can see that the symmetric encryption security, which is weakened by Grover algorithm and which are considering 128-bit quantum security, which is equivalent to 256-bit classical security. So, and in the asymmetric cryptography is broken. So So we can consider the NIST suggested the KEM and signature candidates. And right now we have 8 candidate, and 4 is the in the standardization process. So we can consider them, and we should at least maintain 128-bit quantum security. So here you can see that in the KEM algorithms, we have in the red color are not providing the required security, but the algorithm which are present in the green color like Kyber 768, McAlisi 192, and Bike 192, they are provide at least 128-bit quantum security. Similarly, in the signature category, we can see that D lithium 3 and D lithium 5 Sphinx 256, these are providing at least 128-bit equivalent quantum security. So these algorithm we can use safely. So what are the challenges associated with the deployment of post-quantum cryptography? So there is one of the main challenge is development of standard and protocols, because there is no standard of post-quantum cryptography yet. So some algorithms are in competition. So, and also require the interoperability to work with any system and platform, and also required integrated with the existing system, means they are supporting these kind of algorithms or not, because they have some resource constraints, and also performance and scalability. Education and awareness is required to understand the potential risk of threat and benefit of post-quantum cryptography, and also the cost associated with development and deployment of the post-quantum cryptography. So how hybrid approach address this problem? Because this one is take the advantage of strength of cryptographic algorithm, and they can address the challenges of interoperability and integrate with the existing systems. So how we provide the transiting the quantum resistant infrastructure. So we require a careful planning and coordinations among stakeholders like standardization body, industry organizations, and government organizations. So what is the hybrid? Means we can combine the multiple algorithm. You can see that we have algorithm 1 to n. So we can combine either, at least we require 2 algorithm in hybrid. So we can combine 2 algorithm, we can combine 3 algorithm and n algorithm, whatever we want to make the hybrid solution. So there are some options like you can combine classical cryptography with the post-quantum cryptography. You can combine two post-quantum cryptography with the post-quantum cryptography, and you can combine either one classical cryptography plus two post-quantum cryptography, whatever combinations you want for make the hybrid. So the reason of hybridization is hedging our bets. That means when the security of new primitive is not yet certain, that means the post-quantum cryptography is relatively new and their security is not very well tested, but the security of older primitives is already in questions because of Source and Grover's algorithm. The security of older cryptography is reduced or broken. So that is the reason we can go for the hybrid approach. And to achieve the security and functionality both in post-quantum aware and in backward compatible way, we can use the hybridization approach. So this approach can reduce the risk during the transition, and it can protect with the combined security of classical and post-quantum algorithm. So the benefit is it achieves the security by combining multiple algorithms for better security. At least one of the parallel algorithm is secure. That means we can say that our system is secure. It guarantees the security before quantum. And the hybridization approach is retaining backward compatibility, means we can use with the classical system, and it can leverage the existing infrastructure. They enable the parallel uses of two independent cryptography schemes, or more than two schemes can be used in parallel, and that also support the compliance and provide smooth transitions, flexibility in choosing the algorithm, and adaptability as well. So there are, these are the potential applications for the hybridization approach, like we can use in key encapsulation mechanism, digital signature in key exchange, and as well public key infrastructure. So these are the appropriate security properties for the hybrid scheme, like unforgeability and non-separability. Unforgeability means it ensures the signature can only be generated by the authorized signer, and no one can forge. Uh, this one means the attacker can't be forged the signature. The non-separability means the post-quantum algorithm in which if someone has the someone has the public key and signature, so they cannot derive the private key from that information, and because it is protected with the combined security. And collision resistant, that means it is computationally infeasible for an attacker to find two different messages that have the same signature. And similarly for non-repudiation means it ensures the signer cannot deny having generated a particular signature. So how can we hybrid can be realized in backward compatible way? So we can use the combiner, that combiner approach, to make the combine the KM to realize how we can use the classical and post quantum algorithm together. So these are the KEM combiners, like we have multiple KEM algorithm, like one algorithm, two algorithm, and n algorithm. We can use the combiner to combine them to make the stronger resulting scheme. So if the resulting scheme is secure, as long as one of underlying primitive is secure, means for example, you have multiple locks. If one lock is secure, then your system is secure. So we have many robust combiner exist like hash functions and KM, and these combiners are concatenation, XOR, key derivation functions, and PRF is pseudo random functions. So how can you construct the hybrid signatures? So for hybridization, we require at least two or more signature schemes. So you can choose the multiple signature schemes with the different cryptography properties, and then has the message, and that message is encrypted with signed with the all of these multiple algorithms, and then the final results should be combine, and that the combined result signature is the resulting signature is the hybrid signature, and later you can verify it. How can hybrid signature be realized in popular standard and software, ideally in backward compatible way? So we can use in X509 certificate, in TLS SSH protocol as well. So I will explain later how the X509 certificate provide the hybridization approach. For the signature combiner, we can combine the multiple signature using the combiner. So the resulting scheme is robust. And so how can we combine these algorithms? So if the resulting scheme is secure, then we can say that under our system is secure. Even so, if one signature is strong, which are unable to break by the attacker, that means the resulting scheme is secure. So there are many robust combiners for hash and signatures like concatenation, nesting, and dual nesting. So here, for example, there is a sender and receiver. So sender, in the sender end, what happened? We need to sign twice, one with the post-quantum signature, another with the classical signature. And at the receiver end, a verifier should verify both the signature, both post-quantum and classical signatures. So these are some security notions like what are the type of adversaries? So here X is represent the adversaries of classical or quantum, either C or Q, during the period of time which it can interact with the signing oracle. And the small c and small q represent the whether the adversaries can interact with the signing oracle. And after the period of interaction, it will represent by the z, which is either c or q. So here you can see that this one is fully classical and this one is fully quantum. But this system is attacker has before the classical machine, has the classical signing oracle, and after that they have access of quantum machines. And here the attacker has quantum machines before and after, but they are interacting with the classical signing oracle. So there are some implication and separations between the unforgeability notions like B implications A. That means every B secure scheme is also A secure. Means all quantum secure, fully quantum secure schemes obviously is classical secure. But there is a separation B. That means there exists a secure scheme that are not B secure scheme. Means we cannot guarantee that all classical secure scheme are quantum secure. So the goal of non-separability is misrepresenting the signer original intention to prevent an attacker from taking an hybrid signature. So how can hybrid signature scheme be used in standards? So for example, X509 certificate. So we have the certificate. So in the certificate, we have some managing and revocation rules, and CA can issue the certificate that can bind the public key and sign with their own private key. So TBS certificate, that is a to be signed certificate. It's not signed yet. It has some informations like version number, serial numbers, signature algorithm identifiers, public key, and extensions, so many things. And the TBS certificate, the TBS informations in the certificate will be signed by CA private key. Now it is complete certificate. So the challenge is certificate can only contain exactly one TBS certificate. So we cannot put two subject public key and two signed twicely, because it has only one public key and one signature. So these make backward compatible hybrid certificate challenging. So this is a challenge. We cannot put two public key here and cannot sign twice. So for construction of hybrid certificate, we require two public key, one for traditional and one for post-quantum algorithm, and two signatures. So what are the approaches we can use to create the hybrid algorithm? So this is the certificate. We can utilize the X5093 certificates. So the first approach is we can use two certificate, classical and post-quantum, and each sign with the CA key with the classical signature and post-quantum signature. Another approach is you can use second certificate in extensions. So in the X509 version 3 has the extension field. We can create the post-quantum certificate and put into the extension field and sign it with the classical signature. So in this way, we can create the hybrid certificate. And another approach, we can use only the required field like public key and CA in extension field rather than whole certificate. So these are the some approaches. We can use the Libox library to implement the quantum resistance cryptography algorithm, and it provides the wrapper class to, so you can use in Python, Go, and JavaScript as well. And there are some mechanism for creating hybrid key exchange and signatures. We can combine ECC with Kyber, RSA with dilithium. So we did some experiments and find the result that in the combinations with RSA, Sphinx is required, huge overhead. Similarly, for encryptions and key exchange, in MAC LEC required around 3000 time overhead. So there is a large public key and signature cause the problem, because there is compatibility issues, like some system and protocol have some limitations. There is computational overhead and performance degradations, also reduce the network bandwidth, and storage requirement is increased. So these are some recommendations, like organizations should start and prepare the migration plan to get rid out of the old insecure cryptography and put themselves into the right positions for ready for migrations. And the summary is to achieve the high level of security against both classical and quantum attack. We should consider the hybrid approach, and it support the backward compatibility, but it increase the additional pre-processing and overhead expenses. It can decrease the performance, and the one of the main thing is required modifications in the current standards. So these are my references, and thank you very much. If you have any question, please ask.
Thank you, Dr. Vikas, for that wonderful talk about cryptography, quantum cryptography especially. And since we are running out of time, we can take few questions. And we have one question from the attendees. What is the basis on which one can say that symmetric cryptography is not in danger?
Yeah, because let me start from asymmetric cryptography. Asymmetric cryptography depend on the factorization problem and discrete logarithmic problem. That are some mathematical computations which can easily broken with the quantum machines, because quantum machines has the exponential power compared to the exponential computation power compared to the classical machines. But in case of symmetric cryptography, the we need to break, we require all the combinations of brute force attacks. So we require 2 to the power n combinations, and it can reduce up to the half using that. So in this way, the symmetric cryptography is reduced up to the half, and it not be completely broken. If we are using the longer key size, it will still survive.
Thank you, Vikas, for the explanation, and thank you very much for the nice presentation. As we are on time, I have few notifications. First of all, we would like to thank Dr. Vikas for his time and dedication to deliver this talk at the Cybersecurity Awareness Month webinar series. Once again, thank you, Vikas.